Come on in, everybody.
Good afternoon, Mr. Younger.
How's it going?
Good, how are you?
Not too bad. You excited about being back in physics?
I'm ready to hit it harder than last semester. Like this, I'm feeling good about this one. This is the one.
This is the one. That's excellent. I'm sorry about having to start off this way, everybody. I really did not want to force y'all to take an online class for the first week or two, but it looks like it might have to happen at least. Well, it's definitely going to happen for this week, and it might happen for next week. But after that, it'll all be just a regular class. So I apologize in advance, and hopefully we can get through it. Anybody have any questions? It looks like I recognize a lot of names, but not everybody I've had before. So if you haven't had me before, I will just tell you that because of my surgery situation, not everything, well, I like to say because of my surgery situation, not everything's available, but Elijah might tell on me and say, it wasn't ready last semester either, and I didn't have surgery then. So, but in general, yeah, I should have everything posted tonight, including the syllabus and all that good stuff. It's currently loading the Pearson stuff. So once that comes up, that actually might come up during class, then I can even access the ebook and the homework. So the ebooks and homework should probably be available probably within the next 30 minutes or by the time the class is over. The syllabus might take a little more time, but it'll definitely be up tonight. Worst case scenario, you can log in first thing in the morning tomorrow and find it. But either way, I'm working on that. No real changes last semester other than last time I had distinctly said the midterm was worth a certain percent and the final was worth another percent. I just went ahead and said the comprehensive midterm parenthesis S final exam is worth 55%. The point being that I'm going to try to give you 3 face-to-face tests so that I can drop 1, which is sort of what I usually do anyways. Only I'm going to tell everybody ahead of time that, yeah, we're going to try to shoot for 3. And that way I can drop the lowest midterm, not the lowest final. Of course, there's no dropping of the final. And then you only be graded for 55% of your course grade from the midterm, one of the midterms, and from the final, both of which are comprehensive. I'm still waiting for this to upload. I know I had more students than this. It looks like I only have 6.
Mr. Younger.
Yes.
Darren just texted me. He says he's in the waiting room. If you can't see him, though, I'll let him know to restart.
Yeah, he's got to restart. It's not showing me.
Okay.
Yeah, that's kind of a bummer. Yeah, I've only got 6 people in there for some reason. Also, you might tell him make sure he did the one for lecture, not the one for lab. I don't know if it establishes a waiting room for a meeting that hasn't started yet. It shouldn't, but it might have.
I just told him. He said he's trying it again.
Sounds good. We're not too pressed for time. We have a really short lab for Wednesday. And then we have lecture, of course, Wednesday. The short lab is basically a review of Excel. So even if I cover 0 material today, I'm not too upset just because I have a lot of time next time to play catch up. I see a couple of people, like I said, that I didn't have before. So I'm curious, for those of you I didn't have, did y'all have thermodynamics in your course, or the 241 equivalent course that you took wherever you took it and whoever you took it with? Y'all can respond to that in the chat or just speak out.
Yeah, Justin and I both at Regent University did not have thermodynamics covered.
Okay, that's cool. There's Justin and
Mark.
Gotcha. So y'all were at Regent, you say?
Yes, sir.
That's cool. They had a physics instructor over there now. I'm glad they've got one. They probably had one for a while, but I hadn't been in the loop on that for a couple of years. Okay, got a couple more people. We're way up to 7. And still not seeing Darren now. And I keep hitting the reload for my modules page to see if the stuff I copied over from the other course is coming through. I haven't seen it yet though, so it might not be.
Yeah, he's in the right link, but he's gonna try his laptop now for some reason because he's in the waiting room again. But if you can't see him, then I'm not sure.
Yeah, that's weird. What is that? What's happening? Well, from your own experience, have you had to do that a couple times in your past, Elijah?
I'm on my laptop, but it's worked on my desktop just as much. So I don't know.
Because I have some students that show up initially and everything's going fine, but then they pop back in and out several times during the class. I wonder if something's been dropping them out, or if they originally just weren't getting in because of the waiting room or what. But here we are. All right, we're getting some stuff now. So I now have the link for interesting science related links. They're all there. And I have the link, the module for helpful documents and links. So that's there now. The syllabus is the old syllabus. I'll leave it up there for a little while for you to see it, but it's not the right one. So don't assume that's the right one. I will axe all of these once the correct one's posted. In fact, let me go ahead and I'll kill that syllabus now because I don't want that to get convoluted with the true syllabus. So I'm going to go ahead and turn off those old syllabuses. And I'll go ahead and turn on that module. Looks like everything else should be good. Hating that it's making me hit the button 2 or 3 times now to get stuff to publish and unpublish. Well, that's what it's doing. Yay. So that's up there. The chapter practice is posted as well. So there's a module called chapter practice. And that's basically your ability to, or gives you the ability to take I think it's 3 or 4 question quick quiz on a given chapter. And it doesn't go to my grade book. It doesn't go to your grade book. It just basically is your chance to practice that particular homework set from that particular chapter. So if you're having any homework difficulties for a given chapter, that's the best thing to do. It's a little more focused than the practice test, but that is definitely available. The helpful links, documents, and links is available. The practice test will become available. That's going to be right after the chapter practice. The online test is right after that. That'll come available. And the face-to-face tests are right after that. That'll come available. So far, that looks like all that's been copied so far. But no link from 1 for some reason. I was hoping week 1 would come up because that's where chapter 1 homework is. And once that's posted, then I can actually start to address those things. Yeah, finally now it's up here. So I now have week 1 is available. looks like everything's ready to roll now. All right, so week 1, which is January 8th to January 14th, is now available. Homeworks are available. I'm going to click on them. They're probably not ready yet for you guys, but they will be probably by the end of class if y'all are looking at it right now. Hopefully, well, don't go there yet, but by the end of class, you should be able to go there and everything will work just fine. See if it's 2, there we go. Okay. Okay, so it started making that now, and I also have the ability to go to, I don't know what's happened. If y'all look on your Canvas page, you probably see Pearson at Nova-DE. That's the new My Lab and Mastering link. I sent that to the powers that be to find out why that's now the name. It even went back and changed the name of the link on all my past courses that have already been done. So I know it's something official. I just don't know how they got that. But that's where I'm going to go to open up the document. It looks like I am correct in that no one's covered thermodynamics. So that means I am going to start off this course in chapter 17, which is actually a pretty easy chapter. So that's what we're going to talk about today. Not too terribly much getting started. Glad you can make it, Darren. I see you up there. Darren, did you have a child over the break?
No, that's just my baby brother.
I wondered if it was your baby brother or something. I figured it was something like that, but I thought it was funnier to say you had a kid over the break. Oh, by the way, I just noticed one of the videos from earlier today. For some reason, your video captions that are across the top of my screen were showing on the video, which I'm getting ready to post to my YouTube channel. So I don't know how I'm going to get rid of that, but I want you guys to know that it's going to be up there, and I have to have your permission to put it up there, or I've got to take it down. So y'all might want to just change your names that you're turning in to first name and first initial of last name. And you're welcome to show your image, but like I said, if you're in hiding, I mean, maybe there's some organized crime family that's trying to get you or something for whatever reason. You might want to not show your face until I get that worked out. But do, by all means, if any of you have a problem where you can't have that happen, let me know privately by email, and I won't even put it up until I get that permission from you. So again, you don't have to say it out loud because obviously that would be a sort of moot point. But yeah, definitely let me know if you have any, and you don't have to tell me any reason. Just let me know if you don't want your face or even your whole name put up there. And then to help yourself, like I said, just use your first name and your first initial of your last name and your username for Zoom, and that should help. All right, I've got the area open for the physics documents. I've also got the homeworks open and the ebook open, and I'm going to discuss that a little bit, but first I want to fix the date on the very first one to make sure it's working. Yes, it has chapter 17 homework and chapter 17 conceptual due at 11:59 p.m. on 1/4. Oh, it does not have 11:59 p.m. It has 10:59 p.m. That's not good. But on 14th of January. So I'm going to change this. Okay, now it looks like it's working. All right, so the first two homework assignments have the correct date. They might have a different date in Canvas, but I got to address that too. That just takes a little while. As I said, we are starting in chapter 16. I'm getting ready to do that just as soon as I can get there. Okay, so chapter 17 is temperature, thermal expansion, and the ideal gas law. So we're opening up with just a discussion specifically of the atomic model / molecular model of matter. So originally what happened was, I think his name was Democritus. It's been a while since I studied that aspect of history of science, but I want to say it was Democritus. I don't think it was Anaxagoras, but anyways, an ancient Greek had the idea of matter being basically two scenarios. He imagined that you could take a chunk of matter, let's say a rock, right? And you could take that rock and you cut it in half. Now, if that rock happened to be, in terms of modern day language that they didn't know in ancient Greece, but in terms of modern stuff, if that rock happened to be made of iron, which would be an ideal scenario, or copper, which would be another ideal scenario, or I think y'all get where I'm going with this, or aluminum or something like that, then this would be a best case scenario. And that's sort of what we're shooting at. So imagine that he got a rock that was just happened to be small enough to be pure iron or pure aluminum or pure copper, and you cut that in half. And then you take one of those halves and you cut that in half. And you take one of those halves and you cut that in half and keep on doing that over and over and over again. What Democritus suggested was that there was two scenarios that could happen. One, either you could do that forever, which made no sense to him. There was just no reason he could imagine that would allow matter to be infinitesimally small. So he threw that away just from the logic of it. The other scenario was you would keep cutting that until eventually you got to one piece that you couldn't cut in half anymore. And in fact, the word divisible in Greek was more or less a version of tom. And if you wanted to say not tom, you'd add the prefix a. So it became the atom, which is what we now call the atom. And it's exactly right in those scenarios where I said the rock was pure copper or pure aluminum or pure iron. Okay, it's not so right where you just grab a rock. Okay, because in principle that rock or that chunk of matter that you grabbed could have been a element, which is what we were talking about when we had copper, steel, or aluminum. There's others, of course, but those are the three that I pointed out. That would be an element, and that smallest piece would in fact be an atom. However, you could also have found a piece of titanium oxide. Titanium oxide has titanium with either oxygen or O2, I can't remember, and actually both might be available, but the main thing is that would be a compound. And in fact, you could do that same experiment over and over and over again with a piece of titanium oxide, and ultimately you would get to a smallest piece that you could still break in half, but if you broke it in half, each piece would be entirely different from the other and entirely different from the original. So part of it you'd break would be the titanium, and the other part you'd break would turn into oxygen. And obviously titanium oxide and oxygen and titanium are three entirely different things. So that's a scenario how we sort of modernize what Democritus, if I'm remembering correctly, who said it, but if I'm remembering correctly about it being Democritus, that's what would actually happen. Now, there's a third sort of option too. That thing you pick up could be like a sandwich. If you picked up a sandwich, you know, it has a bread part, it has a meat part, maybe it has a cheese part, unless you're obeying halal or kosher processes, and you're not supposed to mix your milk and cheese. It could have some mayonnaise on it, but that's a mixture. So like a mixture, like a salad, a tall salad's a mixture as well. It doesn't make much sense when you try to apply that process, because when you cut it in half, depending on how you cut it, you could get a whole tomato in a salad, or you could get a quarter of a chunk of ham on a sandwich, or a little piece of mayonnaise on the next one, or a little piece of mayonnaise on bread on the next one, so on and so forth. So mixtures are a little more complicated to deal with, and we don't talk about that at all. But basically, you could take each part that you cut down to the smallest you could get in the mixture, and then that part would be made up of a compound or an element. Now, you can tell if the smallest part was a tomato, then yeah, that's still neither a compound nor an element. Same thing with lettuce. If you cut a piece of lettuce in half and then cut that piece in half and then cut that piece in half, you're going to get a cell. And if it's a single-celled organism, every piece you cut in half is just going to pop out another cell. And in principle, you could still cut the cell in half, but then you're destroying the cell and it wouldn't be anything as well. So there's not much usefulness in terms of mixtures to talk about it. But the main thing is to remember, in terms of the idea of atom as the atom that the ancient Greeks talked about, that was strictly speaking what would have happened to elements. If it was happening to a compound, it would result in the smallest part that still behaved like the original part would be the molecule. And you could still break it apart. So it's not strictly speaking atom, because you could still divide it into multiple parts. In that case, you'd break it up into different elements, and then those would have the smallest part being an element. Okay, so that was a pretty good idea, and he turns out to be somewhat right. And his proof for it was things like when a baker's baking bread, you could smell the bread from some distance away, maybe across the street from the baker, and you could still smell the bread. And what he imagined was those little atoms of bread were floating out in air and would go up in your nose. And turns out he's actually right about that process. He just was wrong about it being atoms as opposed to molecules, and in some cases mixtures. But the main thing is that is exactly the way we smell things. So if your best bud rips one next to you, you're literally experiencing a bad thing, because the molecule that was recently in his butt is now in your nose. And that's not cool. Right? So I always thought it was funny to just say, well, I'll breathe through my mouth. And then heard Cindy Crawford one day on I think it was on the Letterman show. She said, but then my mom asked me, would you rather eat a fart or taste or smell a fart? And I was like, wow, Cindy Crawford's got me on that one. I think I better sniff it as opposed to eat it. So anyways, you guys that have had me before, 100% that I'm chronically stuck in somewhere between 4th and 6th grade. So, all my jokes have to do with poo-poo and pee-pee and boobies and butts and stuff like that. And that's just me being a goober. I hope you find it somewhat entertaining, and hopefully you find it that you can laugh at me, because that's what I'm for. It's I'm supposed to be this person that really knows physics, and you can say, well, at least I'm not the dumb blank that he is by getting his kicks off of making poop jokes. So enjoy that. Now, let me go further with this model. So it turns out that, yeah, these atoms, and if you're dealing with compounds, these molecules are little things that in some sense can't be divided. We now have the ability to divide an atom. We can break an atom up into its constituent parts. We know the atom, for instance, is made up of protons and neutrons in the nucleus and being orbited in some sense by electrons. We know the electrons are fundamental particles, so they can't be further broken down, but the protons and neutrons can be broken down into quarks, and they seem to be fundamental particles as well. But it takes a lot of energy to do so. In fact, even with the initial ideas of quantum mechanics, just taking a rudimentary freshman level calculation, pretending that the atom nucleus is dealing with a force that's infinitely strong, you can see that the nucleus is not going to display itself or break open until you at least apply amount of energy somewhere in the X-rays and maybe even the gamma rays. So that's what we know is required to break an atom apart, but we can do it. And again, it doesn't, once you break it apart, you get protons, neutrons, and electrons, and they're nothing like the original atom. So if you had an atom of iron, That has properties like iron, but when you break it apart, it's got properties of like little bits of electrons and a few protons and a few neutrons. Okay. Molecules, of course, the same way. You break those up into atoms, and then atoms are further broke up. But the big thing is, it turns out that those atoms and those molecules actually vibrate. They vibrate, they move. In fact, you can't really nail them down. It turns out, from a quantum mechanical perspective, it's impossible to make them stop moving, because if you did, you could locate exactly where they are with as much precision as you want, and know that their velocity is zero. And the Heisenberg uncertainty principle says that's not possible. We didn't know any of that. Heck, we didn't even know any of that in 1899. We started to get a hint about that in 1901. And ultimately, we were up to speed on that by probably around 1910, 1920, something like that. Again, I'm a little rusty on those dates, but I just want to let you know that's the nature of it. The atoms and molecules are constantly in motion. They'll never stop. And in fact, ultimately, what we figured out is that this idea of temperature, what you and I call, body temperature, 98.6 degrees Fahrenheit, is actually directly related to that motion. In fact, it's directly related this way. If you take a pure element, for instance, and therefore it's made of atoms, and I'm talking about elements, not oxygen, which would be O2. That's a diatomic element, and that's made up of molecules of oxygen, two oxygen atoms bonded together. So I'm not really talking about that. I'm more talking about like iron, which has individual iron atoms. And it turns out the average kinetic energy that those atoms have in an element is basically within a factor of the temperature of the substance in a very specific unit called the Kelvin. You could also use a very specific unit called the Rankine, but we don't use that. Okay, that's sort of the Fahrenheit equivalent of Kelvin temperature, and it's called the absolute temperature. That's why you normally are not supposed to see it with a degree mark. Degree means arbitrariness. So if you see something marked in degrees, it's arbitrary. That's why, oddly enough, we have degrees in a triangle measured as degrees, but we also have degrees Fahrenheit and degrees Celsius and degrees, various other things. The nature of it is that degree is a measure of arbitrariness. They use 360 degrees for the number of degrees or in a circle, specifically because 360 was a really convenient number. They were using the sexadecimal, or actually, I think they were using sexadecimal. Basically, a base 60 number system was the system that they were using when we first introduced the idea of the degree in geometry. And that is a very natural number to come across, and base 60 is 360. And because it's a very natural number, it's also easily reached by various multiplication problems. So 360 was just a good number, but it's an arbitrary number. It's not based on any data or any evidence or any specialness of the number 360. Similarly, when you say degrees Celsius or degrees Fahrenheit, they're based on the temperature of water, which for us as humans, we know life is pretty dependent on water. We're starting to see a lot of life now that's less dependent on water, but still a lot of life in general depends on water. So we think that's relevant, but we might actually meet a species later on in a distant galaxy or from a distant planet or something like that. It's unlikely that you and I will ever experience meeting someone from a distant galaxy. They're just too far away. But we might meet a species that doesn't need water as much as us, in which case the water seems very arbitrary. So they had to use a degree on that. But here's the cool thing. If you actually make a plot, say, of pressure versus temperature or volume versus temperature, and you make it for water, okay, there'll be a line like this. And then you make it for, I don't know, mercury gas. There'll be a line like this. And then you make it for iron, a large part of which would be solid and then liquid and then all that good stuff. It would be like that. But here's the neat thing. No matter what elements or compounds you use, all those plots of temperature, or excuse me, of volume versus temperature, or pressure versus temperature, either one, with temperature on the horizontal axis every time, all of those graphs would all meet at the same point on the horizontal axis. And that point is the point at which the object appears to have zero motion, appears to have zero volume, appears to make zero pressure. But the fact that all matter points that way means it's no longer arbitrary. And that is the definition of zero absolute temperature. So that turned out to be about negative 273.15, actually 273.15 Celsius. And that's the zero of the Kelvin temperature scale. So what we did with Kelvin versus Celsius is we made a change of 1 degree be exactly the same size. So if I say I'm going to go from 14 degrees Celsius to 15 degrees Celsius, that's the same as going from 273 plus 14 degree Kelvin to 273 plus 15 Kelvin. That's the exact two same numbers. So the size of a degree is the same, only we started the zero down at negative 273 Celsius, and we started the zero of Celsius up at 273 Kelvin. Technically 273.15. The triple point of water is 273.16, but the 273.15 is generally what we use. So that's that system. Now there's also another system where they use the freezing point of water not to be zero like the Celsius scale, and the boiling point of water not to be 100 like Celsius scale, but they use the freezing point of water to be 32 and the boiling point of water to be 212. Anybody know that system? Sounds kind of German.
Fahrenheit.
Yes, the Fahrenheit. So both of those are based on water, but you see the difference. They divided that interval from freezing to boiling up into 100 degree difference from freezing to boiling in the Celsius scale, but they divided it by up into 180 parts in the Fahrenheit scale. 32 to 212. If you subtract 32 from 212, you get 180. So that tells you some things about the Celsius and Fahrenheit comparison. Obviously, a change of 100 Celsius corresponds to a change of 180 Fahrenheit. So you can see a change of 1 Fahrenheit is a lot smaller than a change of 1 Celsius. That's why it's super critical to know the decimal point on temperature if you're using the Celsius scale. But if you're using the Fahrenheit scale, 98 versus 98.6 isn't that big of a difference. But 98 versus 99 isn't that much of a difference either. So you can use that just fine. But if you say 35 versus 36, that's a big difference. Okay. So if you say 35 Kelvin, or excuse me, 35 Celsius versus 36 Celsius, that's a huge difference. So that's something to keep in mind. Now, with that in mind, let me give you a little rundown on what the temperatures we're talking about are. So I'm going to share my, as I figure out what page I'm on, there you go. I'm going to share my screen with you, and my screen will be my iPad. So let me turn that on. Okay, so the first thing I mentioned to you was talking about a graph. And here's an idea what I'm talking about with that graph. We could say temperature right here. And here we could say pressure, or we could say volume, or we could even say kinetic energy per molecule. Doesn't really matter, to be honest with you. And we could make graphs. And in fact, the graphs would look something like this. Let's do, I'm going to do them all in blue since that's what we started with. So basically we have this. And this could be, for instance, titanium oxide. This could be H2O. This could be helium. This could be hydrogen. I could do another one. This could be oxygen. All of those different compounds and elements all have a common point. And it would all the graphs would look like this, whether you're plotting pressure versus temperature, volume versus temperature, or kinetic energy per molecule versus temperature. And then therefore this became absolute zero. And it equals negative 273.15 degrees Celsius, which we define to be 0 Kelvin. Okay. So that's what makes it not arbitrary. That's why I don't have a degree mark there as well. And then we make our temperature systems like this. We say the boiling point of water. And we say the freezing. Are right there. And then what I'm going to do is just add a nice little sort of like a temperature scale, if you will. There's one. There's one. There's one. And there's one. So what I'm going to say is this is 0 degrees Celsius. Oh. And then this would be 273.15 Kelvin. And this would be 32 degrees Fahrenheit. And I can't remember what it is in Rankine, but I'll pull that up real quick. Ordinary 1.67. Okay, so this is the Rankine scale. And then, of course, we have up here 100 degrees Celsius. Here we have 373.15. And that's Kelvin, of course. And here we have 212 degrees Fahrenheit. And finally, if I take 490, 1.67, and I add 180 to it, I get 671.67 Rankine. Okay, so that's Celsius, Kelvin, named after Lord Kelvin, and Fahrenheit. Oh, that went bad. Like that. So those are our temperature scales. What I need you to recognize, of course, is that this is 100 Celsius degrees. Notice how I'll put the degree after the Celsius when I'm actually calculating a change in temperature. So the degree comes afterwards. Same thing here. This is 180 Fahrenheit degrees between here and here. And you also see a change of delta of 100. And actually, I shouldn't write it that way. Say delta is equal to 180 here as well. And I don't put the Fahrenheit on there or the degrees on there specifically because remember, it's not an arbitrary scale, so we don't do that. Now, this also gives us a way to convert back and forth between the units that we use. For instance, you guys are mostly used to using Fahrenheit and very little Celsius, and you need to know how to convert them. Now, I will tell you that the old tried and true way is to use linear equations, y equals mx plus b, because there's a linear relationship between Fahrenheit and Celsius. You could also make this one Celsius and this one Fahrenheit as well. And all you have to do is take these data points, the 0 and 100 and the 32 and the 212, and you can work out that equation. And that works nice. That's the way I did it forever. And I was really proud of myself because I had never been showed it. I just figured out that it worked. And lo and behold, I got the formula that everybody used. And that works great. But we've learned since then, pedagogically speaking, in other words, in the area of research about learning, we've discovered that there's actually a way that students better internalize these temperature systems or these temperature units. And now I'm going to teach you the way they do that. So the better way is to recognize how these scales are related. So if I say, for instance, delta T in Celsius versus delta T in Fahrenheit, then I get the result of 100 over 180, which you can immediately see this would be Celsius degrees, and this would be Fahrenheit degrees. Well, you can also immediately see that I can reduce that by at least getting rid of the factor of 10, and that would give me 10, go back to blue. That'd give me 10 Celsius degrees over 18 Fahrenheit degrees, but that also give me 5 Celsius degrees over 9 Fahrenheit degrees. So those are some different ways we could do it. Of course, you can also say that 5/9 is 0.555 Celsius degrees per Fahrenheit degree. And that's a conversion factor. If I wanted to turn it over, I could say delta T in Fahrenheit over delta T in Celsius is the same thing. It's 180 Fahrenheit over 100 Celsius, which equals 18 Fahrenheit over 10 Celsius, which gives me 9 Fahrenheit over 5 Celsius degrees. And of course, here's where you could use the fact that the way a fifths works is pretty nice. 5 goes into 9 one time. So that would be 1, and then I'd have 4 left over. So that'd be 1 4/5 Fahrenheit per Celsius. That's not really the helpful part. The helpful part is when you put it back as a decimal, for instance. Everybody knows that 4/5 is 0.8. So you could say 1.8 Fahrenheit degrees for every 1 degree Celsius. So those are various ways we can use this information about the difference between boiling point and freezing being 180 and 100. So let me show you how we're going to go about converting this. Now, to be honest with you, I still give my test as multiple choice tests generally. So unless I decide to write in an open response question and tell you to show me your work, I can't tell if you're doing it this way or not, but I do recommend doing it just because it will help you. And the better you get at your mathematics skills, the better off you'll be anyways. So let's see. I would like to convert I'll start with this because I know where I'm going. Let's convert 50 degrees Celsius to degrees Fahrenheit. Okay. So to do that, this is the way I'm going to do it. What you first want to do is, one, how far is temperature from freezing of H2O. And by the way, I'm using freezing because it's kind of close to freezing. In reality, I could use boiling too. So I'll say R boiling. So I'm going to do 50 degrees Celsius minus 0 degrees Celsius is equal to 50 Celsius degrees. See how I've just converted that from 50 degrees Celsius to 50 Celsius degrees? Now I can use those factors. Okay. So 2, how far would that be from freezing in the desired temperature? Okay. Left off with a question mark there. So now I'm going to do 50 Celsius degrees. And what I need to do is look up there and see which one has Celsius on the bottom. Oh, this 9/5 looks like it works pretty well. So I'm going to say 9 Fahrenheit degrees over 5 Celsius degrees. And the reason I chose that is it's completely obvious that 5 goes into 50 really well. So I don't actually have to do any division. 50 is 5 times 10, so that 5 down there will cancel out. So you can see this 5 and this 5 cancel out, and ultimately I get 90. And by the way, the other thing that happens is this Celsius degree cancels with this Celsius degree, so I'm left with 90 Fahrenheit degrees. Okay. So step 3, now we know how far it's going to be from freezing. Use the temperature of freezing to find the temp in that temperature scale. So I know that I'm 90 degrees above freezing. Freezing in the Fahrenheit is 32. So I'm going to say temperature is equal to 90 Fahrenheit degrees plus 32 degrees Fahrenheit, which gives me, of course, 122 degrees Fahrenheit. Now, if we tried our other way, which I can do really quickly, I'm going to derive it just because I don't remember it off the top of my head, never took the time to memorize it because I could always come up with it. What I know is we're wanting to solve for Fahrenheit here. So I'll say F is equal to MC plus B, which by the way, hopefully y'all recognize is Y equals mx plus b. That's going to give me the facts that I know are that when the Celsius temperature is 0, the Fahrenheit is 32. So I can say 32 is equal to m times 0 plus b. And that tells me that b is equal to 32. Now I can say the other one, which is 212, is equal to m times 100 plus 32. That gives me 212 minus 32, you see, is 180. So that gives me m is equal to 180 divided by 100, which is 9/5. So F is equal to 9/5 C plus 32. Now, if I check that, I get F is equal to 9/5 of 50 degrees Celsius plus 32. 9/5 of 50 would be 90. 90 plus 32 is 122 degrees Fahrenheit. Check. So the way we did above the black bar is the way that you should do to learn your own method. In other words, is we found through educational research that this is a superior way of teaching and superior way of learning the Celsius system. Anybody have any questions on that one? I've only done Celsius to Fahrenheit. I'm getting ready to do a Fahrenheit to Celsius as well, though. Any questions? All right, so let's try another. Let's try, what is 100 degrees Fahrenheit in degrees Celsius? So again, I'll say 1, how far is the temp from freezing point of H2O or boiling So what I can see is 100 degrees Fahrenheit minus 32 degrees Fahrenheit is equal to, obviously, it's going to be 68 Fahrenheit degrees. So I can put the degree mark after the Fahrenheit. Does that make sense to everyone? Okay. 2, how far is that in Celsius degrees? So now I'm going to take 68 Fahrenheit degrees, and now I've got to take, well, we did like 9/5 before. It really doesn't matter what we do, but we can choose wisely. And if we choose wisely, then we might actually get to do the math without actually having to use a calculator or anything. So for instance, I could divide 68 by 9, but 9 doesn't go evenly into 68, so that's not very helpful. In fact, not much goes evenly into 68, but what I can do is do 1.8 Fahrenheit degrees to 1 Celsius degree. So that's not necessarily that easy, but I could make it 680 divided by 18. That's not necessarily even that much easier. So I'm just going to throw it in the calculator and do 68 divided by 1.8. And that gives me 37.777. So this is equal to 37.77. And obviously there's some extra sig figs there. But this Fahrenheit cancels out with this Fahrenheit. And then all I have to do is multiply this by 1 Celsius degree. And now I get 37 point, might as well just call it 8 Celsius degrees. Now then part 3, remember part 3 we said use the temperature of freezing to find the temperature in that scale. So use the temp of freezing to find the temp in that scale. So 0 degrees Celsius plus 37.8 degrees Celsius is equal to 37.8 degrees Celsius. And that should be our answer. If I choose again to use the formula I just derived, I can say F is equal to 9/5 C plus 32. I can plug all that stuff in. I'm going to say 100 is equal to 9/5 C plus 32. That gives me 68 is equal to 9/5 C, which gives me C is equal to 5/9 times 68, which gives me 37.8 degrees Celsius. Okay, so we see that in fact this method works every time. And like I said, if you had a temperature of like 240, why would you go all the way back to 0 Celsius, or if it was 240 Fahrenheit, why would you go all the way back to 32 when you could go to 212? So you can use either one. The main thing is this is the process by which you do it. Does anybody have any questions on that? Pretty straightforward, right? Not that big a deal. No one has any questions there, right?
I got one question.
Yeah, go for it. Ab.
Just maybe I missed it, but what is it that significant of a difference with the degrees Celsius and then Celsius degrees? Like the order of those?
No, it's just it's sort of like sort of like tabulating things. Sometimes you want a different symbol just so you can remember what number you're working with.
I got you.
It's just
Okay.
really convenient to put the degree afterwards once you've done a subtraction, and it just
Okay.
helps you keep your wits about you.
Okay. Okay. Yeah, it makes sense now. Thanks.
Yeah, a few books use it, but a lot of books still don't use it. And no, I don't see anybody correcting people when they do it like in a classroom. So it's not a uniform thing that everybody's saying, okay, when you subtract two temperatures, you get Fahrenheit degrees or Celsius degrees. It's not like that at all. I just use it because it helps us.
Okay.
Good question.
Mr. Younger.
Yes.
So when you're adding a degree Celsius to a Celsius degree, that changes it back to a degree Celsius.
Yeah, so that's the little bit of where we took the liberties of changing Fahrenheit degrees and degrees Fahrenheit as if there's something different. But that very fact that you add those shows you that they're not different at all. So it goes back to Adam's question. You're
Okay.
just using it as a tool to help you realize what you did versus what you didn't do yet.
Until you get back to the third. Okay. Okay.
Any questions on that? All right, so that's one of the big things that you got to be able to do with temperature and thermometers. And in fact, to be honest with you, you really only have to find any kind of parameter that changes with temperature and that you can measure pretty well. Once you have that, you can make a thermometer. Basically, what you do is you say, oh, hey, look at this. I just discovered this chunk of aluminum here. When I heat it up, it gets longer. or it gets bigger in diameter when I heat it up. And then I say, okay, well, what's the length right now? Well, guess what? If it went from 70 degrees Fahrenheit to 72 degrees Fahrenheit, even using this vernier caliper is not going to help me. I can't measure that difference. It's too small of a difference, right? So that's a problem. But if you're going from temperatures on the order of, 70 degrees Fahrenheit to 200, then you could possibly measure it. But the main thing is that's a variable that you can use to make a thermoscope. It's a thermoscope up until you calibrate it, at which time it becomes a thermometer. Okay, so length is another thing, and that's one of the things we're going to cover in this chapter. Is it turns out that basically all objects, except for a few, expand when they're heated up and contract when they're cooled down. Another thing that happens, which is more related to what we're going to do later in the semester, is the resistance of metals, of conductors, changes with temperature. And generally, the resistance goes up the hotter it is. You can sort of imagine it like you're trying to shuffle some individual electrons through the wire. And as the wire gets hotter and hotter, all the atoms and molecules are vibrating faster and faster. So it's harder to get those molecules through. That's a way of looking at it. And that's actually one that we can measure pretty well. And in fact, there's a name for it. It's called like a thermocouple, where you can actually use the change in temperature to the change in resistance to actually measure the change in temperature. That's not unlike what they have, for instance, in dryers. You'll notice, for instance, in a typical dryer in a house, sometimes they'll just stop working. Sometimes your clothes come out and they smell like they're burnt. And what's happened is one of the thermistors, or one of the things that measure the temperature, has screwed up. And it's allowing the temperature of the element to get so hot that it's making the dryer temperature too hot. That's a dangerous thing. You could actually cause a fire. I've actually seen literally the paint start to burn off the outside of the dryer. If that's happening, you can imagine, guess what? If I had, like a plastic laundry bin or something like that up there, that could melt the laundry bin, set it on fire. It could melt the laundry bin, set the clothes inside of it on fire, and then your whole house burned down. So one of the things you do when you start looking for that, or when you start seeing that kind of problem, is you start opening up and looking for thermistors or thermocouples or whatever. They normally look like little top hats. So there's like a little round thing shaped like the top of a top hat, and then they'll have like a little flat, instead of like a normal brim, they'll have a brim that comes to a point in one end and a point in the other end. They're often the things that you need. And they're so cheap, you just go ahead and replace them all rather than trying to figure out which ones work. There's ways to figure out which one's bad, but if you don't have the time or don't want to waste the time, you just take them all out, take them to Ferguson and buy a new one. Once they see that, they'll know what to match it with. They find that, you come back, put it back in, making sure you put the polarity right and everything, if there is such a thing. Usually isn't. And the next thing you know, you got your dryer working again. Okay, so anything that changes with temperature can be used. For instance, a solid's not good, but guess what? A liquid is quite good. That's why, has anybody ever seen a liquid thermometer, a thermometer that uses a liquid to determine what the temperature is? Hopefully you've all seen that. You're awful young, so you might not. Okay, so yeah, you're probably at least heard of thermometers where they have a little red liquid in it, or sometimes they have shiny mercury in it. They're trying to get away from the mercury because mercury's not all that healthy. But like I said before, I told you that we've been able to track, I can't remember, Lewis and Clark. We've been able to track Lewis and Clark and where they traveled across the western U.S. by finding fossilized stool samples with mercury in them. Every time you find one that's fossilized at about the time period they were out there, you can guarantee it was there because the Native Americans didn't know about using mercury as an emetic and didn't have access to mercury as an emetic. So yeah, people have been eating mercury for a long time, and it actually was quite helpful in some cases. So it's not as bad as it seems, but I still wouldn't eat it as unless I absolutely had to. But they use that. They use toluene, which has other carcinogenic problems. They use different alcohols. Those are a lot better. So that's what a lot of them are. But because it's a liquid, it actually expands quite a bit. If you can make the tube in which the liquid sits to be very small in cross section. So it's making like a cylinder, sort of like this. But what you want is the radius to be really, really small and the length to be really, really long. So then a small change in temperature makes for a huge change in the actual length because the volume changes by a significant amount. So that's another way of doing it. Once you get that, you can then say, okay, let me take this device that I've made, maybe it's some blown glass that I poured red alcohol in and then sealed it off. And I take that glass thermometer type thing, I stick it in an ice bath, and then I mark where the top of the red liquid is. I put a little etch mark on the glass there. That's going to correspond to, say, 0 degrees Celsius or also 32 degrees Fahrenheit. Then I do the same thing, this time sticking the glass in boiling water. And hopefully you've got enough clearance so it don't explode. But if you don't, it will explode. I did this one time. I was trying to get out of going to school. I think I was like in 7th or 8th grade. And I was looking for some way to warm up a thermometer so I could stay home. Luckily, my mom had been smoking in the bathroom just that a couple minutes before. So I grabbed her lighter, lit it up, they just busted. So flame's a little too hot. Maybe if I'd been a little less rushed, I wouldn't have done it so bad. But the main thing is, yeah, you put it in boiling water, and if it's got enough room to expand, then it'll expand quite a bit, and then it'll stop moving. And then you put a little etch mark there on the glass, and that'll correspond to 100 degrees Celsius and also 212 Fahrenheit. So if you take the side that has the 0 and the 100, you measure it, divide that measurement by 100, and then use that measurement to go from 0 to 1, make a mark. Use that measurement from 1 to 2, make a mark. Then you've got instead of a thermoscope, you have a thermometer because it's calibrated. You can do the same thing on the other side, but this time you have to divide the measurement by 180. Does that make sense? It's kind of neat how you can go back to brass tacks and make whatever you need for whatever things just because you have a little bit of understanding of physics. That's the main thing I'm shooting for here. All right, so that's temperature and thermometers. Another thing we're discussing here, and we only got about 12 minutes left, is the atomic theory of matter. And I've sort of already hinted at that with the atomic theory of matter. The only thing I didn't really hit on was the idea of the atomic mass unit. So let's go with that. The atomic mass unit, which is given the symbol lowercase u. Now, one atomic mass unit is essentially 1.6605. Notice how I potted those numbers as a pot of 3 and then gave a little bit of space in the next number. That's the best way to do it when you're writing these numbers, so it's easy for me to count. And that's times 10 to the negative 27th. And this is in kilograms, which is important because the way I'm going to teach you, you're going to get this with 10 to the negative like 24th or something, as opposed to 10 to the negative 27th. But what the atomic mass unit is they decided that if you take carbon 12, which is the most abundant version of carbon, and also happens to be one of the fundamental elements of life, right? That's, in fact, organic chemistry is called organic chemistry specifically because it has carbon in it. So whenever you're dealing with atoms that have carbon in it, you're touching on organic chemistry. So what we did was we said, let's define the mass of carbon 12, the most abundant form of carbon, to be 12 unified atomic mass units. That's why they're using the U, by the way. I should probably put that in. Let me write it right here. unified atomic mass units. Notice that corresponds to the U and to that U. So the unified atomic mass units, if you say the mass of carbon 12, let me write it a different way. Is equal to 12.000 U exactly. That's really what we're shooting for. You try to make that an infinite number of decimal places. If you do that, then it works out pretty nicely, because remember, carbon 12 is a carbon atom that has, because it's carbon, has to have 6 protons. And because it's carbon 12, the total number of nucleons is 12. So that means it has to have 6 protons and 6 neutrons. And then remember, of course, a neutral atom has to have an equal number of electrons, but electrons are like 1,000 times less massive than protons or neutrons. So you don't even care about that. So in doing so, you're sort of assuming that the mass of proton or the mass of a neutron is about 1. So that's sort of the argument for it. I'll just remind you, the 12 implies 12 nucleons, which means number of protons plus number of neutrons is equal to 12. And the carbon means I forget what symbol they use, but I'm going to say number of protons is equal to 6, which is the atomic number. Let me rewrite that. Okay. So with that in mind, it seems reasonable for us to come up with the idea of 12 mass units being the mass of the carbon 12 atom, right? But does anybody know what the mass of carbon 12 is from the periodic table?
It's like 12.01.
Yes. And the way they do those masses on the periodic table is they take the percentage of carbon on planet Earth, that's specifically carbon 12, they make that into a decimal, so it'd be like 0.99624 or something. They multiply that by the mass of the carbon 12, and then they say plus, okay, here's carbon 13, its likelihood is 0.01279, and multiply that by the carbon 13, and then the next 1% times the carbon 14, and so on and so forth. They take a weighted average of all the isotopes. So in fact, you can sort of think of it as the reason why that's not exactly 12 is because of those isotopes, right? But one of the units that we use for the periodic table is not just grams. That's normally what we use, right? So when we look at the periodic table, I'm looking at it right now, it says carbon is 12.011. So from the periodic table, you would conclude M carbon equals 12.011 grams. That's one way of thinking about it, but in fact, it's actually grams per mole. Remember, that's why we use it in calculating the molecular weight of various things, or in calculating the number of moles of stuff that you learned in chemistry. Is you take the total number of grams of something and divide it by 12.011, and that'll tell you how many grams of, or how many moles of carbon you have. Does that, y'all remember that? Does that sound reasonable? Okay, so you can agree that we're going to call carbon 12 approximately 12 unified atomic mass units, but carbon 12 is also approximately 12 grams per mole. So how many atoms of carbon are there in 12.011 grams? Let me repeat it. How many atoms of carbon is there in 12.011 grams of carbon?
Just 1 mole.
1 mole. And do you remember what that number is, or at least the name of that number? Starts with an A.
Avogadro.
There you go. Yeah, so basically what you're going to have is 12 times Avogadro's number in the 12.011 grams. So that might tell you something, because it just told you that the mass was 12 grams and that the mass was 12 unified atomic mass units. So you might realize that the unified atomic mass unit, 1U, let me write this in a different color so it stands out. Is approximately equal to 1 over Avogadro's number. Everybody take your calculator and do 1 divided by Avogadro's number. So I'm going to do 1 divided by 6.022. Actually, I'd like a better version. Let me see if I can get a couple more digits. Avogadro's number. 6.023. No, that's not helpful. What about? There you go. 6.02214. So I'm going to do 1 divided by 6.022. One four times 10 to the 23rd, and that's per mole. So that's moles to the -1 power. And when I do that, I get 1.660, and then a 5 times 10 to the -24th. And of course, that is 10 to the -24th, which is really close to what we wanted. And you can see that the difference is the same as the difference between grams and kilograms. So if you divide that by 1,000 to convert it to kilograms, that means the atomic mass unit, the unified atomic mass unit, really is just 1 over Avogadro's number. So you don't even have to memorize that other number, because you already know Avogadro's number. Any questions on that? All right. Well, it's 3:18. Class is supposed to be over at 3:20. I think this is sufficient to get you guys started. Just to recap what we've covered so far, I'm going to tell you that we have covered subsection 17-1 and actually I put 2 of those, and 17-2 and that's about it. Okay, your homework covers all of chapter 17. Of course, it's already available in MyLab and Mastering. You have a 17 homework, and then you have a 17 conceptual. You can go ahead and start those. Those are due on the 14th. Remember, you automatically get a free 2-week trial on the MyLab and Mastering. So even if you don't have the book yet, even if you haven't been able to purchase the access code yet, all you have to do is click on the homework assignment, take the 2-week trial period, and it'll allow you to do the homework now. So there's really no excuse to not do the homework. And in fact, you're always allowed in this course to do the homework up to 7 days late for partial credit. That's what's going to happen if you don't get it done by the 14th at 11:59 p.m. So just make sure you knock that out. Shouldn't be a problem. There's some neat things where you're going to learn how to use the idea that the main thing that I'm trying to get in this last part where I talked about Avogadro's number is that the periodic table in the periodic table. .011 grams means 12.011 grams per mole. And it means 12.011 atomic mass units, unified atomic mass units per atom. So that gives you a lot of power. You can now start counting the number of atoms, for instance, in a chunk of metal. You can start calculating how far apart the atoms are in a chunk of metal. We're going to do some examples like that, and your book will do them as well. But that's what this atomic theory of matter helps you do. The other thing, as I was telling you, the molecules are vibrating and moving such that their average kinetic energy of translation is directly related or directly proportional to the temperature. That's a really big deal. And in fact, as the temperature goes up, that motion goes up. That causes them to find an equilibrium position that's farther apart at higher temperatures. That's why we have expansion at higher temperatures and contraction at lower temperatures. But if you go further, it'll get so hot that a solid will no longer have strong enough inner atomic forces to attract one atom to, I should say extra atomic forces to attract one atom to its neighbor. That becomes too weak and they break apart. And that's transitioning from a solid to a liquid, where one atom will sort of roll over the other atom for a period of time and then slowly move away and start rolling around another one and slowly move away and start moving towards another one. That's where, when you're a liquid. If you do it further, the temperature, the equilibrium distance between two atoms gets even larger, and you have still too little force to even keep them near each other for a split second, and that results in it breaking apart to make a gas. So that's the last of the big atomic theory stuff and how it's supposed to be applied. Hopefully that'll help you. We will jump into section 17.3 and do thermal expansion, the zeroth law of thermodynamics, volume expansion. I'll talk about the anomalous behavior of water. Remember, I told you just about everything expands when you increase its temperature and contracts when you decrease its temperature. Water mostly does that, but there's a weird area around the freezing point of water where it doesn't do that. And thank goodness, because we would have went extinct during ice ages if it wasn't for that. So that's kind of neat. We'll talk about thermal stresses, the ideal gas law, and that's pretty much it. And then we'll jump into chapter 18. You guys are free to go. I'll wait for the last person to leave in case you have any questions, but thanks for coming, everybody. Let me stop this. Anybody have any questions?
I just wanted to double check, like, as far as last semester, everything's gonna be pretty formatted, like the practice test, equation sheets, and all that stuff.
Yeah, I'm not changing anything majorly. I do have now an equation sheet for 241, which you're just not in time to have used, but by the time this semester's over, I'll probably have an equation sheet for 242, so you won't get to use that either. I'll try, though. I'll try to get it ready for you.
Sounds good. Well, you have a good day, Mr. Younger.
You too, Elijah. Nice seeing you. Nice seeing you, Darren, and Marcus.
seeing
and
you.
guys.
You have a nice
Thanks,
day.
Professor.
Adam.
Thanks, Professor. Have a
Nice
good
meeting
one.
you, Mark, and I forgot the other person's name. Tyler and Andre. There you go. Good luck, everybody. Have a nice one.